All right, welcome to the last chunk of content for Calc 1. We're going to introduce this idea of what an antiderivative is, and that's going to lead us into indefinite integrals. Integrals are the third of the big main topics in Calc 1. We first start talking about limits. We build up an idea of continuity from limits, and then we build up an idea of a derivative coming from a limit. And then we talk about derivatives for a long time. And now we're going to talk about antiderivatives and integrals. And so integration will be our last big chunk of content that we have. So we're going to start off with just introducing the idea of what an antiderivative or a family of antiderivatives is. We're going to build up some notation with this integral. Then we're going to find antiderivative families for a bunch of function types. All of our rules, we'll just get a list of things that we already know. The nice thing is that we're pretty familiar with this already because there's going to be a really easy link to derivatives. And then we'll end things off with an initial value problem. So that should go pretty well. Here we go. We'll start off with antiderivatives and families of antiderivatives. So here's the main idea. An antiderivative function is just something whose derivative is the function we care about. So this is one of the things I try and show a lot. We normally start with a function, f, and what we do is we find the first derivative eventually. And then we end up talking about that. We learn a whole bunch of derivative rules, and then we say, well, wait a second, this first derivative is a rate of change. What about a rate of change of a rate of change, right? What about the second derivative? And we talk about the third derivative if we want. We don't really do that too much in this class. We talk about how the first derivative is slope and the second derivative is concavity, and we could try and think of what the third derivative is. It's kind of like the rate of change of concavity. What you'll notice is that instead of plunging forward like this, we're going to go backwards. It's really hard to move forward and keep a visual idea of what's going on here. So instead, we're going to go back to our function and we'll say, well, what about the thing that could have come before it? And we'll call this thing capital F, and this is what an antiderivative is. What you'll notice is that for capital F, the derivative of that function is the same thing as little f. And the second derivative of that function is the first derivative of little f, and so on and so forth. So we can kind of just offset these by 1 by saying, all right, instead of taking this function instead of taking this function here, I wanted to highlight that, and finding a derivative of it, let's take this function and say, what would we have had to differentiate to get this as the answer? So what is the first, or what is this the first derivative of? So that's the general idea of what an antiderivative is. So here's a bunch of examples. The main key here is we're trying to figure out what function did we have to find the derivative of to get this as an answer. So pause the video. These three shouldn't be too bad because we can check our answer, right? Once you get a possibility, a solution here, just find the derivative of it and make sure that it ends up being 3x squared or 2 cosine x or 7 secant squared x plus 1. So there's a little bit of trial and error maybe, but we'll probably get used to this pretty quickly. Pause the video, give that a try, and then we'll fill it in a second. All right, so hopefully, my guess is that you probably got something like this. Capital F is x cubed, and the reason is because the derivative of that thing is 3x squared by the power rule. And we could look at this and say capital G of x is probably 2 sine x. And that's because the derivative of that would be 2 cosine x. And then lastly, we could say capital L of x is probably 7 tangent of x plus x. Because capital L prime is just going to be 7 secant squared x plus, not plus x, plus 1. There we go. So again, really easy to check your answer here. These are not that complicated, which is good. And the reason they're not that complicated is because we have a lot of intuition about the first derivative already. Now, there certainly will be some instances where it's going to be really hard for us to try and figure out what could have possibly been differentiated to get this as an answer, as the first derivative. But these basic examples aren't going to be that big of a deal. So maybe actually I'll go back. Don't read that yet. What I want to do is challenge you to pause the video again and see if you can come up with a second answer for all of these. A different function, not just x cubed, not 2 sine of x, not 7 tangent x plus x, where if you take the derivative, you still get the same things. So pause the video, see if you can come up with an alternate version for a capital F. Notice in the definition of a derivative, it says the function is an antiderivative, right? Not the antiderivative. It's like one of the antiderivatives. So it's possible that there are more, and I want to see if you can find them. Pause the video, see if you can give that a shot. All right, maybe you figured this out, but maybe not. A lot of times students have a hard time thinking this through, and it's because the answer is almost like an obvious but seems like cheating answer. What we can do is say, well, what if we let capital F of x be something like x cubed plus 7? This adding 7 certainly changes the function, but the derivative isn't going to change because the derivative of 7 is 0, right? Or what if we did something like g of x equals 2 cosine x minus pi? Pi is just a number. When you find the derivative of that, oops, not 2 cosine x, sorry, 2 sine x. There we go. Pi is just a number. When you find the derivative, that's going to go to 0. This part is still going to give us that 2 cosine x. And we could say capital L of x is 7 tangent x plus x, I don't know, plus 11 thirds. Notice it doesn't really matter what this number is. Could be positive, could be negative, but if it's just a constant, it's not going to change the derivative. So this introduces this idea of families of antiderivatives. So if f is some antiderivative of little f, then all of the antiderivatives of little f are going to be in that form of capital F, that function that we found, plus some constant. So we'll normally write it this way. And we normally will call that constant like a constant of integration or something like that. But if we go back, then what we could say is really capital F of x is 3x squared plus c. And now this is a whole family of antiderivatives. And capital G of x is, oops, oh my gosh, I forgot to actually write the antiderivative. It's x cubed. There we go. And then we have 2 sine x plus c, and then L of x is 7 tangent x plus c, where c could be anything. So this just helps us not have to write out every single possibility with every single constant that we could imaginably get, right? So if we just add this plus c, that wraps everything up. Let's try and think about what this visually means. I like to draw this picture when we talk about this. Let's say that here's some antiderivative function, capital F of x. What happens when we add a constant or subtract a constant, or add a negative, I guess, to this function? What does it do to a function when you just add a number right at the end? Well, it shifts the function, right? That's a vertical shift. I'm really bad at drawing this, but oh well. So here's another version of that same function, just shifted. And here's another version of that same function, just shifted. And maybe there's some down here. And maybe there's like another one down here. And there's this cloud of shifted functions up and down that could be infinitely close to each other because we can make that constant be as small as we'd like. Maybe we just have a tiny shift, so it's almost the same thing as our blue function, but whatever. So let's try and get this concept here, right? What we're looking at is trying to figure out what f prime of x is, capital F prime, because that's what little f is, right? And we want that to be the same. Well, let's go ahead and just draw a line straight down. And let's look at the point on each of our graphs here. Now, these points all have the same x value. What should be true, if my drawing was any good, is that all of these points have a tangent line with the same slope. Now, it's not going to be true in my case because my drawing is kind of crappy, but oh well. You could imagine that if we haven't changed the shape of our function, then we haven't changed the slope of it at a point. And so we're saying we can shift this function up or down as much as we'd like, and it doesn't change the slope at a point. If we haven't moved things left and right, then all the x values are going to have the same kind of behavior, or that x value on every function is going to have the same kind of behavior there. The tangent line is going to have the same slope. So that's the main idea that we've got with these family of antiderivatives. You can visualize these things as kind of like a cloud of functions that are all identical to each other. They're just shifted up and down. Okay, let's introduce indefinite integrals then. This is just like a purely notational thing, so I'll go ahead and just label all the pieces here, and it's just a way of writing out what we're talking about without having to use words. This is the same as when we used to say like, oops, let me get rid of that straight line. When we used to say things like the derivative of f of x equals 4x squared is f prime of x equals 8x. A different way of writing that is just using this derivative notation. And that says the exact same thing, but we don't have to write out the whole sentence, right? So that's what this really is. This is an integral sign. This is the thing that's telling us we're thinking about integrals. We're going to be thinking about antiderivatives. This function here, little f of x, we call it the integrand. It's the function inside the integral. This is the thing that we're going to find the antiderivative of. Find antiderivative family of this. This dx is a differential. It's got a couple of roles. The first and most obvious one is that it is the end of the integral. It's like the parenthesis that closes this thing out that says like, okay, find the derivative of 4x squared, and now once you hit this parenthesis, you're done. It's like the period at the end of the sentence here. So it tells us what's inside our integral. This integral sign is like an open parenthesis. This differential dx is like a closed parenthesis. It also, I'll just add this down here, tells us what the input variable is. Now, most of the time, that's going to be pretty obvious for us because our functions have the same input variable. But that way, if there's a whole bunch of unknown values, you know which one is actually going to be the variable we're using. That means if you've got some function that has like t as an input variable, that differential will look like dt instead. There's also going to be a nice geometric representation or understanding of what that differential is. And so we can think about that a little bit later. And then this thing is our antiderivative family. And the plus c specifically, we call that the constant of integration. So again, all of this is just a notational way of representing what we've already been doing when we find these antiderivative families. So if we take a look at those same three examples, we can really just say, all right, what this is saying is find the antiderivative family of 3x squared, and we know that that's going to be x cubed plus c. Find the antiderivative family of 2 cosine x. Well, we know that that's going to be 2 sine x plus c. Find the antiderivative family of 7 secant squared x plus 1. That's going to be 7 tan x plus c. If we don't include the plus c, then all we've done is found a specific antiderivative, but we want the whole family here. So make sure that we always include that constant of integration to represent the fact that this is really holding an infinite number of functions in this one little expression. All right, so at this point, we can pretty much just start running through our list of functions that we know and write out formally all the antiderivative families. This is not going to be difficult because we're very familiar with derivatives. Some of these we might have to think about a little bit, but probably not that much. So we'll just start with constant functions. We could take a look at an example if you want. We've already done one, but let's take a look. All right, we're really saying what function do we have to find the derivative of to get 7? Well, that's pretty easy. 7x, and then we'll add that plus c for our family. So for constant functions, it's just going to be kx plus c, where k is some constant. Hey, this makes sense. When you find the derivative of a linear function, we just end up with a constant. All right, for the power function, this might seem a little tricky at first, but let's go ahead and just do an example. Let's go x to the 4 dx. See if you can find a function whose derivative is x to the 4. Pause the video, give this a shot. If you want to look back, we've already done one for 3x squared. Now that's a little bit different than what we have here. But oh well. Take a look, see what's going to be different. Hopefully that's helpful. All right, probably what you noticed is that we know this function is going to be some sort of an x to the 5th function, right? Because then when we find the derivative, we would bring this, oops, I don't want to do a dotted line. We would bring this thing out front and subtract 1, and 5 minus 1 is 4. But the problem is then we'd have this coefficient of 5. So we got to figure out a way of undoing that coefficient because we don't want it there. And it's pretty easy. You can just multiply by a 5th. That way, now when you bring that 5 out front, 5 times a 5th is really just 1. Subtract 1, your exponent is 4. So what we'll do is we'll say your function is going to have 1 more in the exponent. So we'll call it n plus 1. And we're also going to divide by that value. That way when we do the power rule and we bring our exponent out front, we've got n plus 1 over n plus 1. That's really just 1. Notice there's no coefficient here. The coefficient's really 1. So that's what we've got. Hopefully you can see why we have this little requirement. Don't let n be negative 1, because if it is, and you add 1, you're going to get 0. Okay, that's a little bit weird. So what this means is now you could look at another example, something like the integral of x to the 15 dx, and we know we'll just add 1 to our exponent and divide by that value. You can easily check your answer here by just making sure that the derivative of x to the 16 over 16 plus c is equal to x to the 15. And if it is, you're good. I should probably put my parentheses there. There we go. So that's not too bad. All right, so let's take a look at the case when n was equal to negative 1, right? This reciprocal function. And we'll say, oh, okay, I know what's going on here. We're trying to find a function whose derivative is 1 over x. That's going to be the natural log function plus c. Now, you might notice I put some absolute values on here, and that might seem a little tricky, but let's talk about really briefly why that is. Here's a log function. Here's 1 over x. When we found the derivative of the log function, the domain of this function is 0 to infinity. The 1 over x function, the domain is negative infinity to 0, union 0 up to infinity. But when we found the log's derivative, we were thinking about slopes of tangent lines. It only made sense to plug in positive values. So we really didn't consider this negative side, right? It doesn't make sense to say, oh, when x is negative 2, the slope on the log function is negative half, right? 1 over negative 2. That doesn't make sense. There's nothing over here. And so we don't talk about slopes of tangent lines there. So what we do is we kind of restrict the domain to just this part. We don't really look at this. We got to do the same kind of thing here. Now we're starting with this 1 over x function. The domain is all these real numbers except for 0. We like to be able to make the domain of the antiderivative function match. Now, instead of restricting it, we have to extend it. So I throw these absolute values on. So at the very least, if you put a negative in, we'll just look at evaluating the log at the positive version of that. So this is just to match up domains. That's all. There's really nothing going on here. All right, let's talk about exponentials. The easiest case is going to be obviously this one. What function do you have to differentiate to find e to the x? Well, that's going to be pretty obvious. E to the x and then plus c. Let's just remember our derivative rule for the general logarithm. Or sorry, the general exponential. we're going to multiply by the natural log of the base. So if we want to find a function whose derivative is just b of x, just this part, we want to cancel out this log, you'll notice that we can divide by it. This is similar to the power rule where we divide these things out to cancel things, extra coefficients. That natural log of b is a coefficient on the derivative. If you find the derivative of this thing, the derivative of b to the x is b to the x natural log of b. The natural logs will cancel out, and we just have this b to the x. Cool. We mostly will deal with the exponential e to the x. We probably won't see a lot of like 2 to the x and 4 to the x and stuff like that. All right, trig functions. You can just go ahead and like knock these things out, honestly. The thing that we'll find the derivative of to get sine, we got to be careful. Normally, the derivative of cosine is negative sine, so I'm going to write negative cosine of x plus c. That way, when we find the derivative, we have negative sine. There we go. The thing that you find the derivative of to get cosine of x is sine of x. We'll notice that secant squared is the derivative of tangent x. Secant x tangent x is the derivative of secant x. And then you'll notice that this is almost the derivative of cotangent x, but the derivative of cotangent x is negative cosecant squared x. So we'll say this is negative cotangent x. And then similarly, we'll have negative cosecant x plus c. You'll notice that right off the bat, we don't have things like this. I don't know a function, I mean I do, but we collectively don't know a function whose derivative is tangent x. And we collectively don't know a function yet whose derivative is secant of x. We will investigate some of these. Some of them we'll do this semester in Calc 1. Some of them we'll leave for Calc 2. It's all going to be dependent on how far we end up getting and stuff. But these are normally some trickier ones that we'll have to look at a little bit more carefully. Similarly, with the inverse trig functions, these themselves aren't inverse trig functions, but we might recognize this as the derivative of sine inverse. You might recognize this as the derivative of tan inverse. And you might recognize this as kind of the derivative of secant inverse x. Oops, let me fix this. I need my absolute values here. There's a similar thing going on with the logs. Normally we have an absolute value here, but to match domains up, we can throw an absolute value in the secant inverse function. I'm not going to go into too much of why that is, but you can kind of mess with it if you'd like. It's really just a domain matching thing. All right, here are some general properties. If we have coefficients, it shouldn't surprise us that we can factor those things out. This was something we were able to do with derivatives, so it makes sense that we can do that with antiderivatives. And oops, I didn't want that coefficient there. I'll get rid of that on your version of the blank notes. This one, similarly, with sums and differences, we'll be able to split those things up. So we'll look at the integral of f of x, add and subtract it with the integral of g of x, find those things out individually, put it together. We've already done this, though, in our examples, so this should be pretty good. So let's just take a look at some random examples here. Let's do something like 4x to the 7 minus 6 secant x tangent x plus 8 over, I don't want to do 8 over 2, that's just 4. I'll do 8 over 3 x dx. I might rewrite this a little bit. I might call this 4x to the 7 minus 6 secant x tangent x plus, just so we can see it, 8/3 times 1 over x dx. All right, so what we can do is split this up into 3 integrals. Oops, dx minus 6 secant x tangent x dx plus the integral of 8/3 times 1 over x dx. And then we can pull all these coefficients out, and we've got 4 integral x to the 7 dx minus 6 integral secant x tangent x dx plus 8/3 integral 1 over x dx. And then for each of these, we can find antiderivatives using our properties above. Now, sometimes we might say that, well, each of these is going to have a constant of integration, right? So maybe we'll say like the first one, this x to the 7, has a c1, and the second one has like a c2, and the third one has like a c3. All those constants are just going to get added together. And so what we'll do is we'll just wrap it up all at the very, very end with just one constant c, because we can add all of the random constants together to get some other constant. All right, so what do we end up with? We've got 4 times x to the 8 over 8. Add 1 to the exponent and divide. Minus 6 times, we might recognize this secant x tangent x as the derivative of secant. Plus 8/3 times, when we see this reciprocal function, that's going to be this natural log with an absolute value. And then I'll tack on my plus c. Oops, I wrote an x in the denominator here. This is 4, or 8, I mean. There we go. Now we can say, okay, this is really x to the 8 over 2 minus 6 secant x plus 8/3 natural log of the absolute value of x. What you'll notice is that you can pretty easily just jump right down to this step if you recognize all of these properties along the way. So that's fine. I'm okay with that. But that's how this looks. All right, we'll finish this up with an initial value problem. This is just one little wrinkle where we may not end up with a plus c at the very end, and it's because we're going to be able to solve for what the specific constant is. So remember that picture that we had? Where we had like, okay, here's our antiderivative that we found. Oh, shoot. I want that to be gone. There we go. Here's our antiderivative that we found, and then we had this like cloud of the shifted functions, right? All above and below it, and they all were identical, just like my perfect drawings are. They were just moved up and down. And what we're saying is like, what if we have a point here? We'll call it right there. Well, then what we want is the version of our antiderivative that specifically goes through that point. And we can find that specific function. It's like if we throw a dart at this cloud of antiderivatives, what function, which antiderivative function does it stick to? When we put a point in here, which of these antiderivatives are we grabbing? So let's first just deal with this problem here. Let's say we've got a derivative. We want to go backwards to find the antiderivative function. So we can say f of x will equal the family of antiderivatives here, x squared minus 3x dx. And we'll just keep this little bit of information in our back pocket. All right, power rule says we can go ahead and just add 1 to our exponent and divide by that number. So this is x cubed over 3 minus 3x squared over 2 plus c. We can double check this and make sure by saying if you find the derivative of x cubed over 3, the 3 comes out front and cancels, so it's really x squared. And we can bring the 2 out front, and we have 6 over 2, which is really 3. And then the exponent on here becomes 1. Cool, so that works out really nicely. The problem is this is just a representation of all of these antiderivatives, and what we want is specifically the one where f of 1 equals a third. So let's just use this information by putting 1 in for x and setting this whole thing equal to a third. So we'll say a third is equal to whatever happens when you put 1 in for x. And now we have this equation with only one thing that's unknown. 1/3 equals 1/3 minus 3/2 plus c. Hopefully we can see pretty easily that if you subtract a third from both sides, you get 0, add 3/2 to both sides, and c is equal to 3/2. What that means is that the specific antiderivative function that we're looking for is this. What we're given here is specifically this black graph, right? This is the specific antiderivative. It's a function whose derivative is x squared minus 3x. You can check that again. Notice that this constant didn't change anything. And also it meets this requirement of f of 1 equals a third. So if we have this extra requirement, all we have to do is solve for that constant of integration. And that's just algebra. We just have to keep our heads out so we know what we're supposed to be doing here. This is some point on this antiderivative family of functions that we can say, I want the specific antiderivative that goes through that point. So it's not a hard extra stuff that I've done in green here from what we were doing earlier. It's just something that we have to keep remembering, that when you have that extra information, we'll call this thing here the initial value. When you have an initial value like that, we can solve for a specific antiderivative. Cool. That's everything we've got for antiderivatives. We're going to keep going on this topic with integrals and antiderivatives a little bit more, and we're going to try and show geometrically and graphically what they might represent. So that's what we're up to in these next couple of videos. We're going to keep messing around with these antiderivatives and integrals and try and get a nice graphical connection. Cool.